Zoom right now. Let's see. Christina?
Yes, can you hear me?
Yeah, we can. So okay, they have an audio device for us, but it is not working. So I'm just going to play you through my laptop speakers, but I'll crank it when your time is up, okay?
Okay, sounds good.
Okay, yeah, sorry about that. So, but anyways, all right, I just wanted to check in. All right, cool. Thank you very much.
Thanks.
Oh, okay. I think the recording is going. We're sharing the screen. So I think we're good. All right. So, hello everybody. My name is Nick. So I received my PhD a little bit under a year ago from Purdue with Stanley Chan. So I've done a decent amount of work, depends how you define it, I guess, on imaging through atmospheric turbulence, okay, simulating it. And so this workshop, bridging the gap between computational photography and visual recognition, I think it fits well within what have been sort of my research interest for the last, I don't know, few years, I guess. This workshop is a joint effort between a number of universities. Let me go to the next slide. So technically speaking, it is an international group of universities. Okay, now it's only international because two is like technically a club. Okay, but so we have a couple groups from Singapore who are joining us through Zoom today, and then four from the States. So I imagine many of you know where UCLA, Yale is, and UT Austin, because it says it in the name, right? But I'm just wondering how many people here know where Purdue is if I wasn't showing you on the map right now. A couple people. All right, cool, cool. So, sometimes I'm surprised to see how many people do know it, and sometimes I'm surprised to see how many people don't. Okay, because you never know. Okay, sometimes you have to just read the room, I guess. Okay, so all right, so this is where we're distributed. So the organizing team, as I said, technically international, is comprised of five professors: Stanley Chan, Atlas Wong, Ashita Kanabi, Alex Wong, and Bradley Priest. Oh, actually, excuse me, Bradley Priest is from U.S. Army, so four professors plus one U.S. Army DevCom officer. Okay. And as I said, I'm Nick, and then there's a whole host of students. Howard is one of them sitting in the front row here, who've worked on the challenge and all of that. So for our challenge tracks, let me introduce to you what we've, I guess, been working on. Okay, what challenges we've been running. So the very first is atmospheric turbulence mitigation and downstream tasks. I'll talk a little bit about this later, okay, just in this brief introduction here. But the idea with this is that you're imaging through maybe over some long distance. And over this long distance, the wave that propagates from the object to the camera, this is the wave of light, gets distorted by some action in the medium. Okay, this is turbulence, and it distorts the image. So the question is, if you restore the image, can your downstream computer vision tasks still work? Okay, that's the first challenge track. Second challenge track is all-weather semantic segmentation. So this is if I'm seeing through rain or fog or haze or snow and this kind of thing, can I train some sort of method? Semantic segmentation works on clean images. Okay, works really good. Can I train some sort of method to do semantic segmentation on these less than ideal conditions? Okay, so that's the purpose of this challenge. And Howard will talk about it, but a lot of data has been generated and collected and all of this stuff for the sake of this challenge. And finally is the UAV tracking and pose estimation challenge. This one, I have to give them a lot of credit. So as I said, I've done some stuff on atmospheric turbulence. And, mine was mostly, I guess, theory. Okay, I'll put that in air quotes, but it's simulation stuff. Okay. And I always hated going out and having to take real data. Okay. But so this group from Singapore, they actually went out and they took, I'll tell you in a brief moment, an insane amount of data, okay, with so many modalities. It's really quite impressive what they did. Okay, so I'll talk about that in a little bit. So okay, we do have a paper track, so I would just like to mention those people, and you can find them in the proceedings, of course. Excuse me. So we have UAV Rain 1K. This is on raindrop removal from UAV aerial imagery, feature corrective transfer learning, source-free domain adaptation for video object detection under adverse image conditions. Xinguang Zhang, I should mention, is in Stanley Chan's lab, so I know him quite well. Okay, and then the last group is from Samsung Research America. I know them just a little bit. Mobile aware denoiser network for quad bare images. Okay, so these are the papers that we published this year. Okay, in this workshop anyway. So, and then today we have three really great invited speakers. So I'm going to do them in reverse order in the way that they're written because that's the way that they're presented. Okay. So the first person I'll mention is Achyuta Kadambi, who's an associate professor at UCLA. He does computational imaging, non-line of sight, medical applications, time of flight imaging, really quite a number of things. So he will be our first speaker. Our second speaker will be Christina Monacava. She's an incoming assistant professor at Cornell. Currently, she's doing her postdoc at MIT, if memory serves me correctly. She's also worked with Laura Waller. She's done a number of things like diffuser cam lensless imaging, if you guys are familiar with that. They take a piece of tape, put it over a sensor, and then like do some sort of depth aware sensing. It's pretty interesting stuff they do there. She's also done some microscopy stuff, really a number of things. So that's our second speaker. And then the final one is Minchul Kim. I'm wondering how many people in here do facial recognition or detection or anything like that? Number of people. So Mitchell just within the last year or two, I know him pretty well, released this ADA face with Anil Jain and Xiaoming Liu from MSU. So he's a PhD student at MSU, but I think his paper ADA face has really gained some traction within, I would say, this community and kind of what's that Windshare conference on what is it, WACV, right? I couldn't think of it. Yeah. But so facial recognition, so he'll be talking about that. So each talk will be about 30 minutes, 25 minutes, and then 5 minutes of Q&A. My plan is to leave questions for the end of those talks. If the speakers feel otherwise, I will say they'll let you know. Okay. So anyways, yeah. Okay, the schedule, I pretty much just told you, but you can find it on the website. This is the schedule. I won't dwell too much on that just for the sake of time. Okay, so now let's get really to what this challenge is all about. All right, so this is computer vision. Okay, so I don't have to tell all you guys. All right, but object detection works pretty well. Okay, a new form of YOLO comes out, I don't know, every so often. Okay, you guys would know better than me. And it works really well for your training data sets. And I would say many of you would define this as deploying it in the wild, right? So you strap it on a car. What does the object detection perform on the car? So this challenge looks at something a little bit different, which is, what if I really have, I mean, to just say it bluntly, crappy data, okay? That's really the goal of this challenge. What if my input is absolutely terrible relative to the pristine data that we're used to? And how does it impact my downstream computer vision tasks? So one project that I'm like funded by right now is through IARPA, and it's biometric recognition in imaging at range, okay? So it's a fancy way of saying detecting people through turbulence over a distance, okay? Now, why does a guy doing image restoration turbulence have to work on such a project? It's really to answer, to me, what I consider to be a pretty core question of this community, which is, can image restoration boost your downstream, let's say, facial recognition or, just general computer vision tasks? I think that's actually, it sounds like the answer would be yes. If I make the image on the left look better, you would expect, right, the recognition would go up. What we tend to find, seriously, overwhelmingly, is that that's actually the opposite of true. Normally, an image that looks good to you or I will actually hurt the downstream task. I think this can be, again, this is very turbulence specific, okay? And some of the other challenges address other things. So I don't wish to give you the impression that this is the whole point of the challenge, okay? But just because I know a little bit about it, okay, I'll figure out to talk about it. This is a pretty surprising result because you would think this would improve it. But what we accounted to be is a few things. One is a bit of a training data mismatch. If you're training your input data on clean data, restored data is just by definition different than clean data. There are artifacts in it, there's over smoothing. So there's a bit of a distribution gap, right? And second, each restoration method is a little bit unique, okay? So maybe produce two outputs that look really good, but the little teeny tiny artifacts that they leave in there are completely different. And this seems to significantly negatively impact downstream restoration. Now, so my group, okay, we've been working on turbulence for a while. As far as I know, out of all of the 5 or so performers in this Breyer program, the recognizing people over through turbulence, we're the only ones who are able to make restoration actually improve the computer vision tasks, and it's only on a subset of data. So this is a really difficult problem, but I think an important one is that we need to sort of combine our image restoration and downstream tasks if we're going to make really a coherent system that improves the object detection and recognition and so on, right? So that's really one of the fundamental questions of this challenge, is just pushing the edge of where we can apply our computer vision algorithms in 2024, okay? And so on. So, all right, let me talk about then what exactly we were having people do in the imaging through turbulence track, okay? So the first one is text recognition through atmospheric turbulence. So in Indiana, okay, which is not, it can get hot, but it's not like Arizona, okay? So in Indiana, we set up a target maybe 500 meters away, big camera, and we took some videos of printed text on a piece of paper, again, about 500 meters or so. And what we observed was the thing on the left, okay? So you can see it's shaky and it's temporally varying and all of these things. And the idea is, well, there's no ground truth that you can ever get back, right? Because once I've observed it at that distance, I'm never really going to get the same exact conditions. So ground truth is pretty much out, okay? So we have to use something sort of in place of the ground truth. So it'll be text recognition, right? So if I can recover the sequence of data here well enough that I can reconstruct what the text is if I just send to some downstream text recognition tasks. How can I perform? So that's how we're going to rank performers on the first challenge, okay? Is how they improve the text recognition after the restoration. The second, and I have to give credit to this guy I talked about earlier, Bradley Priest, is a coded target restoration through atmospheric turbulence. How many of you have seen that Snapchat demo where it's like a depth varying QR code? Has anyone seen anything like that before? Have you, maybe you have? You have seen that? It's really interesting, isn't it? Okay, so what it is based on how well you can resolve the QR code, okay, you get some sort of score. The further, the better that you can resolve it. So close up, you can get the score really high. The further back you move, it becomes worse. This is really a very similar idea, just in a slightly different fashion. And so you have some sort of, it's essentially a QR code with circles though, okay? And the idea is that you compute what it's supposed to look like, and it has, what it's actually supposed to look like, and you compute the Hamming distance between these two things. So in effect, it's giving you a QR code that you're computing the distance in some sort of odd space, binary space, okay? So this is the imaging through turbulence track. So what do we provide to the performers for this imaging through turbulence track? Well, we have a couple from our group, Stanley Chan's group. We have a couple restoration methods. And actually, so let me show you, just because we have a nice demo. And so I feel like if you ever have an opportunity to show a demo, you should do it, okay? So we have these open source, I'm just trying to scroll here. It's not working. Oh, I think I know why. Yeah, there's a lot on this page. I think everything going on my MacBook is slowing it down. But so let me go to this one. This one's good. So we have some input and then restored. Okay. Input and restored. So all these are available on our website. So performers have access to these restoration methods, but I think more importantly is they have access to the data that we use to train these. I'll show just one more, just for the sake of it. Okay. I always really like doing this back and forth. It's very satisfying to me. Okay. So anyways, I really like that. And I'll close that out now. All right. So as I said, we give them access to that, but I think most importantly, we give them roughly 200 gigabytes of simulated data. So in previous years, we would give them simulated data. Rather, we would give them a simulator, okay? But the simulator is actually really hard to use right because it's truly a simulator. Okay, so all the parameters have to be chosen very carefully. Okay, so but what we've done is we've kind of skipped all that for them and just given them here's 200 gigabytes. Okay, so and then I have to do a little advertisement. Okay, so if you're curious to learn about how the simulator works and all of that, I have a book along with my PhD advisor Stanley Chan, Computational Imaging Through Atmospheric Turbulence. Okay, that covers not only the theory of how waves propagate through the atmosphere and so on, but also what in the world the simulator is doing, okay? Because it works very differently than a lot of the other ways of doing it. And that is a simulated, that I had Xinguang, the guy that I mentioned earlier, send me this. This is one of my favorite videos because it looks, I think, real. You know what I mean? I thought it was real, but anyways, I was happy with that. All right. And then, so now I think Howard is going to talk about his challenge. So, okay, so I've downloaded your slides. So let me flip to them really quick here. All right. And I'll pull it up and all that. That's good. Yeah. All right. All you.
Thanks so much. All right, just a quick introduction, I guess. I'm Howard. I'm currently third year going to my fourth year as a PhD student in Professor Atruda Kadambi's lab. So I'm going to be talking about semantic segmentation in degraded weather conditions. So first of all, I guess we all know what semantic segmentation is. It has a rich history and a bunch of different applications, so it's definitely a task that we care a lot about in the vision community. So recently in recent years, we've seen this explosion of like foundation models or like models trained on like just billions of images, right? And they perform really well on semantic segmentation as a task. And specifically, they perform really well on clean images for semantic segmentation, right? You can see down there, you can see an example of semantic segmentation currently in natural clear weather conditions. And we are really good at this specific task now. Is it just, oh yeah, okay. So the issue is once you start introducing different sorts of weather conditions like rain or fog or snow, these semantic segmentation models start performing really poorly. This distribution gap between clear images and degraded images from weather conditions starts really lowering our accuracy, our MIOU, intersection over union metrics, right? So why is this such a difficult task to solve, right? It's essentially because weather is a really complex condition in the real world. So weather effects can be particularly complex because they're dependent on all sorts of things, like what sort of camera you're using, what sort of the atmospheric conditions you're looking at, even geographic locations. Like rain will look different in like certain parts of Asia compared to certain parts of North America, right? So it can also manifest as like a bunch of different effects, right? It can be like droplets, streaks, like snowflakes. It can be haze if you're looking really far at something, right? So the purpose of our challenge track is to study weather phenomenon in the real world to try to spark novel ideas that will help semantic segmentation in these degraded weather conditions. So in order to do that, we need data sets, right? We want to train our neural network models. We need data to train them. So in order to do that, we've collected this large data set called WeatherStream and WeatherProof for semantic segmentation. So I'll give a little background as to how we collected this data, and this is the data that we provide to the participants in our challenge track. So originally 1 year ago, we collected this data set called GT Rain. That was around 20,000, 30,000-ish images, and they were degraded and clear image pairs, right? Because we want our kind of like ground truth to train our models on, right? And the idea is that it's really difficult to collect this ground truth because if you think about it, you need to take a picture of a scene that's like raining and and then you have like a corresponding clear image, like at the exact same instance in time with the exact same scene, with the exact same like conditions and everything. The only difference being that there's rain in one and then it's clear in the other, right? So in our physical world, that's impossible. So what we did is we employed something called time multiplex ground truth. And what that basically is we download a bunch of data from a bunch of different live stream sources, a lot from YouTube, and then we wait for the weather effect to right as it's about to stop. we capture 300 frames of the weather effect, and then we capture the clear ground truth. So this ended up taking a lot of time. So what we did was we automated the process using WeatherStream, where we used a bunch of like light transport principles to collect hundreds of thousands of these pairs. And if you're interested, you can check out our paper, WeatherStream Light Transport Automation of Single Image Weather. So for the weatherproof data set, we provided semantic segmentation labels on top of this in 10 different semantic classes, and this is what we use for our challenge. So I think the next slide is the results.
I'm wondering how you're gonna, yeah, perfect. All right,
Yeah.
cool. That'd be great. So, okay. Now in the interest of time, I will, let's see, end this show here. So, oh. I feel like I'm having a brain fart. Why is this not, all right, sorry about that. Okay. So now I'll very briefly just detail the last challenge, and we'll come back at we'll go on a break at like 10:30, come back at 11, so we can give them their due diligence, okay? Because they've done a lot of work. So the final challenge is UAV tracking and pose estimation. So what this group, the two groups from Singapore have done is they've taken radar, audio, stereo vision, LiDAR, all of these things, and fisheye lenses and all these stuff, and produced an incredibly large multimodal data set, okay? And the goal is, given all this data, it's seriously like a huge chunk of data, can you track the UAV correctly, estimate its pose correctly, and also estimate which drone it is. Okay, so that's the goal of this final challenge. Okay, this is seriously a ton of data, this one. So I have to give them a lot of credit. 150 gigabytes, okay, of all of this stuff. So okay, and then I'll just end with this, and then I'll introduce the first speaker. So we had 206 participants with roughly 550 total submissions. Okay, so so thank you to everybody that participated in the challenge. That was we seriously appreciate it. So I was like, I feel like there's one more thing. Oh yeah, okay. Thank you. Okay, so that's where I'll end mine. Thank you for listening to my little spiel here. Okay, and then now let me introduce the first speaker. Good. Okay. So our first speaker is Achyuta Kadambi from UCLA. His talk is going to be computational imaging for vision-based digital health. So Achyuta Kadambi is an associate professor at UCLA in electrical engineering and computer science. He leads a laboratory at the intersection of computer vision, computer graphics, AI, and computational imaging. He's the recipient of a lot of awards. Okay, so I really did need this. Okay, this list here of early career awards, including the NSF Career Award, DARPA YFA Award, ARO, IEEE HKN Under 35 Award, and the Forbes 30 Under 30. He's co-founded two California companies to commercialize research technologies. One is Akasha Imaging, which was a perception-driven manufacturing startup that was acquired by Alphabet. That's Google parent company, right? Alphabet, I think so. And then the other is Vayu Robotics, which is currently a Series A company working on perception-driven robot navigation. And he's recently authored a textbook, which I knew before this, okay, computational imaging with Ramesh and Ayush, I think. So available as a free download from MIT Press. So, all right, I'll give the rest of the time to him. Can I ask you, did you join the Zoom? If not, it's okay. I'll stream it over this thing.
Yeah, I can actually just give you the, it's actually Google Slides link.
Oh, yeah, okay. I'll follow along with that. Okay, yeah, sure.
I'll send it to you then.
All right, sure.
I can present off your computer though.
Oh, yeah, sure. Yeah, that works. Yeah. Sorry, I'm not thinking. Yeah, you said you emailed it to me?
Yeah.
Okay, yeah. All right, cool. Would you rather do it from PowerPoint or Google Slides?
Google Slides would be great.
Oh, really? Okay, all right. See, I don't like, personally, I don't like Google Slides, so I always try to do it in PowerPoint. That's why I asked. Probably give it a minute. But... The speed of email, right? Isn't this great? Well, I don't know. I'm sure it's coming, but would you, just for the sake of saving you some time, would you rather just do it from your computer?
Can, but, all right.
Yeah, I don't know. It should be in slow, I guess.
No problem.
I don't know. If it comes up in the next like 20 seconds, I'll let you know. But otherwise, I'll let you do it. You and I have all this if you need it. But
Great.
yeah. And don't worry about the zoom. I'll point it towards the thing, and yeah, we'll be fine. Good.
Okay, so good morning. Let's confess, I a little sleepy because I made the mistake of working out on intelligent with a grad student in her lab, so that has thrown me off a little bit. Actually, it's Sasha, who you'll see in this talk. Talk title is Health Equity and Computational Imaging. And before I start, it's all the work is done by students at UCLA. So this is a picture of our group with kind of past and some present members. And of course, many thanks to our sponsors who support the research. So the purpose of this talk is to talk about how computational imaging or CI can address issues algorithms alone cannot solve. And the running example I'll use here is blood volume estimation. So by the end of this talk, you'll perhaps learn more about blood volume than you wanted to. Before I begin, this is just a nice slide on computational imaging that's credited to Christina, who's going to be one of the speakers later on. And it discusses how it's really a full stack approach, all the way from the imaging system up to the algorithm, and then of course, metrics that we look for on the high level task. Now, in the era of data science, a lot of this needs to be kind of thought. We need to rethink how the imaging system operates, rethink how the algorithms operate, and even rethink the mapping to high-level tasks in this era of data science. So with that dashboard, we're going to organize the talk in 3 layers, the sensor, the data, and then the algorithm. The running example that we're going to be using is plethysmography or blood flow estimation. Plethys kind of means, I don't know Greek very well, it's all Greek to me, but it means volume. So it's like volume over time. So graphy is a measurement. Plethys means volume. So it's a volume of a quantity over time. And so typically in medicine, this word has been used. So it means blood volume over time. The blood volume over time is useful because it can give you medical applications, which we won't discuss in detail here. Heart rate, AFib, arrhythmia, and blood pressure. But the nice thing about a project like blood flow estimation is you can use computer vision or even coursework. So we teach in some of our classes at UCLA how you can use just ordinary camera frames and extract these physiological signals. So this is a photo from a previous paper by Dan McDuff, which discusses how you can use a camera, just an ambient light source in the subject. If you just look at the image frames over time, and maybe you plot a bit of the frame, then you can actually see the oscillations in the individual pixels in each color channel. Now, these oscillations are extremely noisy on a per pixel basis, so you'll typically average a patch or a region of interest, and then process that to get these physiological waveforms. All right, so that's the context, and that's the problem we're going to address today. Before I do that, let me play this quick video. Many of you may have seen it. The light-based soap dispenser. So what's happening here is there's a person with darker skin that's trying to trigger the dispenser. They cannot. And then they use a paper towel, which is brighter, reflects more light, and then now they get the soap. Tries again with the hand. And it doesn't quite work. So this is an example of bias that occurs at the laws of physics at the light transport level in a device, in a medical device or similar. Of course, we're interested in challenges grander than a soap dispenser. Things like plethysmography, pulse oximeters, the thermometer, face recognition as well. But this talk is specific to plethysmography. Now here's plethysmography on Sasha, the student that wore me out yesterday. So Sasha is sitting here, and he's hooked up to a health monitor on his left finger. And then there's a video being captured as well. And we're going to just crop the video to this region of interest here, which is the face. We're going to mask out the eyes. So we're really drawing from the cheek pockets and maybe a little bit of the forehead and processing that data to actually estimate the heart rate. This is in blue. This is time versus arbitrary units. The independent variable here is blood volume. And you can see that it closely matches actually the actual instrument that you measure from a clip, a handheld clip in the hospital. And if you actually track the heart rate, you get 96.7 beats per minute when the ground truth was 96 beats per minute. So being within 1 to 2 beats per minute is clinical accuracy for this particular measurement. The problem happens when you have a darker skinned subject. So if we replace Sasha with a darker skinned subject, now you can see that the waveform is not as clean and the heart rate error is close to 10 beats per minute. So that's a 5-fold increase in the error for this particular problem. This is outside of clinical accuracy, and it would be said that an instrument based on this principle would not give you a valid measurement. It would have to be thrown out for this particular subject. And so in particular, if you actually run this on a very large data set, you will see that if you look at the actual instrument threshold, the Association of Medical Instruments has a threshold that failure is basically when you're 10% off from ground truth. You can see that there are 6 times as many subjects with darker skin that are not supported by the device. So the solution here is a paper where Sasha is the first author along with Pradyumna and Adnan in SIGGRAPH 2022, which is to combine radio and light measurements together. So if the light measurement is biased, just like the soap dispenser, then bring in another physical principle, which in this case is radar or radio. Now, the first question we would need to address is how does radio get you this waveform? And it's actually quite indirect because light actually interacts with blood. So just like when someone is blushing, you can see them. That's actually you visualizing their blood. If they've embarrassed at a party or if they've been drinking alcohol, they'll have a little bit of blood that you can see. But radar doesn't interact with blood. The wavelength of radar is too large to interact with blood molecules. So for that reason, the measurement principle for radar plethysmography is a little different. So in this picture, you have a live medical image from someone's heart beating. The key thing to note here is in this region of interest, you actually have a little bit of motion in the chest wall. There's very little motion. It's like 250 microns up and down, involuntary motion that you're all making every time your heart beats. That's about 10 widths of a human hair, and it's also underneath your clothes. It's underneath your shirt, even if you're wearing a sweater or a jacket. So in this particular case, Sasha is in front of the radar, wearing his UCLA athletic pullover and over another t-shirt. So you can see that there are small chest vibrations that are happening underneath 2 layers of clothing, but the radar can actually pick that up because it won't interact with the clothing. So it'll actually go through and you can actually get a waveform very similar to the blood volume measurement. The problem with this waveform is it's not as accurate. It's not nearly as accurate as the light-based measurement, but it's not interacting with blood directly. And as you can imagine, it's not interacting with anything molecular. So it's not interacting with skin pigment either, which is a molecular phenomenon. So the idea from the SIGGRAPH paper was to simply combine, do sensor fusion. So you can just concatenate the RGB video and the radar data, which would be a range matrix. You concatenate them together, and then you regress a estimated waveform for the blood volume. And the loss that you apply on this is a PPG specific loss, which has some physiological principles as well. Now, the problem with doing this naive fusion by just concatenating the data is that you're going to bring back the inequities from a light-based measurement and mix them with the radar measurement. So the biases that we had in light will still persist if we perform this mixture. So we implement kind of this principle here, which is has a very strong political kind of undertones of how it's interpreted, not taking a side one way or another, but here we apply a colorblind approach. Our principle here is that the waveform, if the instrument is working correctly, you should not know if the waveform is from someone with dark skin or light skin. You should, in this case, be race blind or ethnicity blind or skin color blind. So you should not be able to tell the skin tone of the subject. And to implement that, we just apply an adversarial loss as well. So this adversarial loss, you should, a good kind of fusion, a good way to fuse this fairly, would be able to trick this discriminator that's discriminating between light and dark. So now if we go back to the dark skin subject, it's not as good as the measurement from Sasha, still not nearly as good, but you can see that the estimated heart rate is much closer. It's within 2 beats per minute. So there's a larger scale test that were done, blind Altman plots to identify kind of where the equity and performance lies. But the take-home message is it's not just about skin tone. That's just kind of one very narrow view of equity in a device and light transport. There are many other devices. You can imagine many devices that look at subsurface blood would behave differently on morbidly obese patients that have layers of subcutaneous fat. Okay, so we discussed the sensor briefly in this problem. Let's discuss the data. So one of the biggest problems with this research paper was collecting the data, especially in a semi-COVID kind of time that this research was conducted. So Sasha would actually have to wheel this cart into the medical center, and you would have patients who, in the flow of their regular treatment, would be like, yes, I want to volunteer for a study in the midst of everything that's going on. And so it's quite hard to get, the 91 subjects that we did. So that kind of got us thinking about synthetic data for this problem. Can we create synthetic data? Now, the problem with synthetic data is even though there are a lot of deep fakes, which are, we condemn all bad uses of these, just to be clear, but even though there are a lot of deep fakes out there, the deep fakes, they're designed to spread misinformation, but they're not actually physiologically correct, as you would imagine. So if you actually plot pixels of the PPG, like the platysma graph that we discussed earlier, you're not going to get that clean signal that you got on either Sasha or any real human. In fact, it will have no real association with heart rate. And so in general, if we wanted to embed a time-varying flickering basically into the video, how would we do that properly? So we thought this would be simple. We thought you just take a time-varying signal, like take someone's heart rate at some frequency and multiply the video with that, and then you can have that subtle flickering there. The problem with that is multiplication in this way is too trivial. There's a spatial and light transport complexity to this problem, much like what Howard was discussing earlier, where the physics is so rich that neural nets, if you use this as synthetic data, neural nets are going to get confused. They're not going to grab onto the right principles. So in particular, there are different pockets of blood, bone structure, all this kind of stuff affects the face. So what we do is we actually take a random image in PPG. We don't quite do a simple multiplication, but we do a UV map, which is a 2D projection of the 3D mesh of the face. That creates, you can then take that UV map and regress a blood decomposition where you can estimate pockets of blood in the face. Then you can apply temporal modulation when you understand the pockets of blood in this 2D projection of the 3D world. So basically that gives you a little bit of the geometry and blood cues. And those two factors give you what you need to actually do flickering properly. So now you have these digital humans, sort of. They don't look super aesthetic. That wasn't the goal. They're just used as a farm for synthetic data. But the flickering is quite accurate and representative of real subjects. So how good is it? Well, the proof of the pudding with synthetic data is to then go and evaluate it in the real world. And so the point is that if you actually train only on synthetic data, you're actually within 1 beat per minute. So, and you can also address a lot of the equity issues. You don't solve them because you can actually simulate subjects with different levels of skin tones, right, in the simulation world. And as you would imagine from many, many themes and projects out in the community, when you train on synthetic and real and you mix the two, you really then reach your state of the art. So what we're going towards is maybe the human digital twin project, where you can actually start to simulate more complex features and facets of biology. That's kind of down the road, but this talk is more about PPG. All right, so that's the data. And then finally, we'll briefly discuss the algorithm. So here's another subject. You may be able to recognize the subject in the room. And come to your PhD at UCLA, we'll experiment on you. That's basically the punchline of this talk. But here, remote blood lithography is challenging. This subject has kind of a beard and darker skin, and the lighting might not be quite, quite what it is. And so you can get actually still pretty incorrect measurements from light-based PPG. And in particular, if there's somebody wearing sunglasses and a mask, a surgical mask, like you would in COVID or perhaps at CVPR, then it'll fail because you won't know where to grab the region of interest, right? You can kind of hard code something that this may be a skin and useful, but that might not be quite generalizable. And so you can see massive errors if somebody were to wear sunglasses and a mask and then try to estimate their heart rate using typical methods. And so there's the physics-based methods, which is largely a Fourier transform frequency-based. And then there's the learning methods, which are which kind of are not able to, which overfit to people not wearing masks, right? So how do we make PPG work for optically challenging scenes? The idea is to separate out all the occluders, like a mask, the sunglasses, makeup, face paint, whatever. Separate those all out from the actual blood oscillations. So perform an isolation of the blood components. And you want this to work on different types of skin tones as well as part of the theme of the talk. Some of the more exotic things here is you can see a subject has half a mask, like Phantom of the Opera. You have another subject here that this is actually a secondary reflection in a window. This is not a direct image of the subject, it's actually a window reflection. So the mathematics of PPG, it's just basically a transient signal and a steady state signal. That's what it is. The pixel color is made up of the illumination intensity multiplied by specular plus diffuse, the addition of the two, plus a noise component. And so if I look at this formulation, the specular and diffuse components, which are spatially and time varying, contribute to appearance, but only the diffuse component contributes to blood. Because the blood is underneath your skin, you're not going to get a specular reflection from blood. So your appearance, then your color over time, is appearance plus blood plus some noise term. Let's forget the noise term for now. But let's just think of the appearance as the color as being a sum of appearance and blood, AB, right? A plus B. And so we have a sum of A plus B, and we just want to isolate B, which is the blood. Okay, that's kind of our goal and our problem statement. Now, how do we obtain these A and B decompositions? Just to be clear, if we can decompose B, which is just the blood component, then you can probably process that directly and get the blood signatures from that. That would be like a good isolation. So here we turn to the implicit neural representations. I won't review this because it's very widespread in the community. But the point is that you can compress the space and time signal into a video-based appearance. So you can use basically a video-based NeRF, video-based NLP formulation to effectively get the appearance component. But there's actually a problem with this. The problem is that neural representations are too good. So they're so good, they jointly can actually fit, they compress, if I just take an input video, they compress the whole video into the weights of the neural net. Okay, they do it really well. So it compresses both the appearance and blood variations together. So you're just compressing a regular video. And if I do PPG on this clean subject, I see 0.3 beat per minute error, which is really good. So it is the weights of the neural network, when I decode them, they are still encoding the blood volume oscillations. So somehow we want a neural representation that encodes appearance, but not blood. So to do this, we instead of using the standard NeRF style positional encodings, we changed the encoding to add this phase term here. We add phase terms to each cosine and sine. The phase terms then allow some translation or shifts, which then cause a misalignment in a transient signal. So if I do that now, this is actually good. Even though you see a lot of error here, this is actually a good thing because I'm able to reconstruct the appearance video, but I have high error in the blood flow. So the observation here is that phase encoded representations cause huge error in estimating the blood flow. And this means that because the video looks qualitatively pretty good, then we're only capturing appearance in this framework. So we still don't have a way to capture blood directly, but we have a way to capture appearance and blood, and we have a way to capture appearance. So if we can have A plus B and A, then naively, you can think of having one radiance field, which is the vanilla radiance field, to capture both appearance and blood, and does it really well. And then apply this phase perturbations in the encoding to fit only the appearance. And so then the crude solution is subtract radiance field 1 and radiance field 2, and then isolates the blood component. There's some details about the speed of this, applying hash encodings. Hash encodings are not suited for phase perturbations. So there's some tweaks there, but the basic idea is that you can get from that input video of the subject with a mask and glasses, you can decompose it into the appearance video and a blood video. And if I look at the blood video and I pick a region of interest on the blood video, if I pick an ROI in the blood video that corresponds to where you expect blood to be, you actually do see transient oscillations. But if I pick a patch on the mask, there's not enough signal here because there's no oscillations happening. There's no blood flow on the mask. So now if you actually estimate PPG using the blood decomposition, you can get 1.9 beat per minute error, which is far more accurate than previous methods for the optically challenging cases. So if you look at kind of the out of distribution, we're kind of thinking about this as an out of distribution medical estimate. We kind of are in the top right here. You can apply this to regular videos as well. You don't have to have optically challenging because it automatically just extracts the blood flow, blood estimation, and it happens on different skin tones as well. So here you can see that you're getting really close, almost 0 beat per minute error, and now 0.3 beat per minute error. These signal strength maps here on different conditions, you can actually show that you're picking up. If I actually take the blood video and then I just take like a magnitude of that video, then I actually end up getting maps that correspond to what we expect. So like this person, this subject here is wearing a clown costume, and you can see that the parts where they don't have the face paint have high signal, right? And then you can see this in various contexts. You can also see that a subject here that has darker skin actually has a lower magnitude overall of blood flow that's apparent than a subject with lighter skin. Then you can do some second order analysis by changing lighting and looking at different configurations and basically seeing how strong your blood flow maps are. So with that, let me conclude again by thanking the core team that was involved with a lot of these projects concurrently. There's 3 papers discussed here. Work was really spearheaded by one of the physicians at UCLA, Dr. Laleh Jalalian, but also we discussed Sasha, and then also Pradyumna. Much of his thesis is based on this work. Okay, before I close, I just was on this Delta flight here, and I was thinking about what is an open problem for 2024 that's been on my mind. And there's this like paradox we have with these exotic imaging setups. The big data revolution, right? Whatever you want to call it, foundation models, it's typically for less expressive imagery, like ordinary 2D photographs. If you can couple this with generative AI, you can do like really powerful things just with 2D foundation models. So there's no shade that's being thrown on this 2D kind of framework. But it's also true that a lot of the exotic hardware setups that are built in laboratories, for example, the full 7D planoptics function, looking at polarization, time of flight, and wave hyperspectral, and many others, is the right solution for many tasks. But there's no data engine for these problems. Okay, so they might actually, if you work in a company, you can imagine a bake-off internally, and the 2D camera wins over the 7D camera because it's got an ecosystem of segmentation, semantic segmentation, and everything associated with it. So this is a CI paradox that we will need to think about, I think, in this era of scale. So with that, let me end the talk.
All right, and then are there any questions from any of you guys? I'll let you handle, but.
Yeah, Ilya.
I was gonna ask sort of the CI paradox, because like I think this is the thing everyone maybe thinks about a lot. How much of a like gap do you see between the less expressive big data of like UINT8 RGB versus going to like, if you did this whole thing again with I assume you're using like 8-bit RGB videos.
Yeah.
If you took that to 16-bit RAW, you had like a Sony mirrorless, would you get better measurements? Is that also like a large gap, or is the gap really between like 2D and 7D?
Yeah, so there's papers that are in the community a lot from Ayan Chakrabarty, looking at different types of basically color encodings, low-level parameters, and how that impacts the high-level task. Even the papers do show some variation, but in my opinion, the variation is slight between these. Especially when many of the high-level tasks are semantic based, and then it's pretty far divorced from the low-level parameters. Yeah.
Oh, very interesting talk, thanks. So when you say like data engine, I guess there's like a lot of options, right? So for example, OpenAI has Sora, which is just like generate videos with like no particular model. But like in your talk, you give an example where you have like a very explicit model and you can use light transfer to render up data. And I guess like where do you see for like computational imaging? Are you gonna like have like a blend of those two approaches, or maybe just you favor like model-based stuff because like it's higher dimensional, you can't gather as much data? Like what do you think?
Yeah, I think the question is about whether there'll be kind of blend between model-based and kind of scale-based approaches in computational imaging.
Yeah.
I think there'll always be model-based approaches, but like take this problem as an example that you posed. You can never really get a scale-based problem, right? Unless this takes off and, you know, companies really want heart rate measurements and blood flow measurements at scale, then maybe we can see a comparison. But it's actually difficult to compare what we did with scale. So for example, if I just collected a bunch of subjects with different mask configurations and, you know, different sunglasses and different this and that, how is that compare? Unfortunately, I don't have a more responsive answer, but that's part of the paradox, is that we cannot baseline ourselves with the big scale approaches as well, easily.
Here.
So, the data set that you have, what is the value of the data? So you mentioned that we really certain required to study the hard script is that working,
Yes.
and in order to be able to have that and for the data to read. And the computer to
Yeah, it depends on the architecture you're using. So the short answer is 77 gigahertz is the bandwidth, but 77 gigahertz is the carrier frequency, but within the carrier frequency, you can actually shift it. So you can effectively look at phase shifts of about 10 degrees within that.
All right, awesome. Let's thank our speaker one more time for the great talk. Yeah. Thank you. All right. So our next speaker is Christina Monakova. I think earlier I botched your name. It was sort of my nerves. I hope I did it right this time. Okay. So, but anyways, all right. I just wanted to acknowledge that. We'll all hear her probably say her last name in a moment. Okay. I have the same problem with mine. All right. So, Christina, can I ask you to share your screen?
Yeah, let me share my screen.
Okay.
Can you see this?
In one moment we will. And so I'll field the questions for you and all of that. And so don't worry about that as far as like Zoom and stuff like that. And I'll repeat them back to you as well.
Great.
So let me get a couple things set up on my end here. And then I'll let you go. Okay. Let me introduce the speaker as well. All right, sorry, I'm sort of Zoom focused here. Okay. So, all right, so as I said, our next speaker is Christina Monakova. Her talk title is Learning Noise Models and Error Bars for Low Light Imaging. So Christina is a postdoctoral researcher currently at MIT, supported by the MIT Postdoctoral Fellowship for Engineering Excellence, and she is also an incoming assistant professor of computer science at Cornell University. So congratulations to her, of course. She received her PhD from UC Berkeley in ECE. Excuse me, it's EECS. Okay, so that's my Purdue brain leaking into the thing here. Okay, where she was a member of Laura Waller's Computational Imaging Research Group. Her research focuses on making more capable cameras and microscopes through the co-design of imaging systems and algorithms. So, okay, thank you very much, Christina. And let's welcome the speaker, and then the rest of the time is hers.
Thanks for having me, and sorry that I couldn't be there. I unfortunately got COVID last minute. I'm still testing positive, so I had to cancel my travel plans there. But hopefully you all can hear me and I can still give this talk. So I'm really excited to talk to you about some of my recent work on low light imaging. And this is really kind of going to focus on two projects. One is about learning noise models for extremely high gain, very, very dim videos. For photography. And the second project is going to be actually about microscopy and how can we make denoising algorithms robust and trustworthy so that we can use them for science and we can trust them enough to do science. And then how do we actually kind of use error bars to drive adaptive acquisition for microscopy? So, okay, first I'll jump into the first project of learning noise models. And really the motivation of this project is that the best cameras you can buy on the market can take stunning, beautiful videos whenever the moon is present. But if the moon is not out, you have to have really long exposures. And so it precludes the capture of motion at night. And so you can see the Milky Way, but you can't see fast motion. You can't see animal behavior if the moon is not out. So basically, the motivation was that, our cameras on the market can see really well in daylight, all the way through moonlight illumination. But we asked this question of, can we do better? Can we actually push this and have realistic videos with lots of motion in starlight, in sub-millilux levels of illumination? So we really wanted to try to kind of like push by an order of magnitude what we can see in the extreme dark. And so the way we approach this is to say, okay, let's take a great camera. We have to have a really good starting point. And then we want to really push this camera to its limits, set it at a really high gain. So we're going to have these really, really noisy videos, but hopefully see some motion. And then we want to design some sort of denoiser, hopefully some sort of algorithms to denoise these very noisy videos. But the first question is like, can we see anything at all? If we take a camera in a condition where it's starlight and there's no external lights, what can we see? But this is actually not as easy as it sounds, because if you look at most cities, if you take a camera out at night, your iPhone probably has no problem taking an okay image or an okay video in a city, because there's a lot of light. So here's actually the San Francisco Bay Area, and you can see this is a light pollution map. And if you take a look at this chart we had earlier, our goal is to see in sub-millilux, but at night in most cities, you're somewhere between 20 and 50 lux, perhaps, maybe as low as maybe a few lux of light, but you're nowhere near sub-millilux, because you have all of these external lights, you have all the lamps, and you have this glow throughout cities. And so for this project, just to even see how well a camera could do, we had to go out kind of in the middle of nowhere in this place called Point Arena, which I was in the Bay Area at the time I was doing this project, and I was really lucky that we could just drive out a few hours and go to a place that's very, very dark. And so we went out on a moonless, clear night, and we verified with external sensor that it was really dark. We measured between 0.6 and 0.7 millilux of light. And we took a bunch of videos with this really, really nice camera, between 5 and 10 frames per second. Now, as a comparison, I had my DSLR camera with me, and I took a 30-second exposure, and this is all you can see. You can see the Milky Way, and it's very, very dark. But even a very nice camera still needs a really long 30-second exposure to see anything. But now we're going to see if we can shoot videos and capture motion in these extremely dark situations. So, okay, we did this, and here's actually the raw video clip that we're able to measure. So we have this, super nice camera that we set to a really, really high gain, and we have a great lens with a large aperture to collect as much light as possible. And the raw video, we actually can see something. It's very dark, very dim, but we see some motion. And if we contrast stretch this, we're actually able to see a lot of details. The details are, of course, obstructed by noise, but it's a good starting point. So if we can just take these video clips, have some sort of denoiser, we're in business. We can hopefully get some really nice denoised videos of motion in sub-millilux. So we tried to take some off-the-shelf denoisers and see, do these off-the-shelf denoisers work in this really challenging setting? But, unfortunately, a lot of off-the-shelf denoisers assume Gaussian noise, and oftentimes are trained using daylight scenes. So they look very, very different from our raw videos, which are taken under starlight conditions and have very structured noise, where you see all of these sorts of line artifacts throughout the noise. So if we apply an off-the-shelf denoiser to our raw video clips, we actually don't do so well. You still see all of these line artifacts throughout this, so that this is the result of VBM4D, which is a standard classic video denoiser. And if we use a off-the-shelf pre-trained deep network for videos, it also, loses a lot of details and blurs out the whole scene. So we said, okay, obviously this is not going to work because our noise is very different. So how about we just collect a data set of real noisy and noiseless images from our camera? We can set the camera to a high gain short exposure, and correspondingly also collect images with a low gain and a lot of exposure to collect a real data set of noisy and noiseless images. Then we can train a denoiser from scratch to denoise this, and hopefully this will give us a denoiser that works really well for the type of noise that we see with our camera. Unfortunately, whenever we did this, there's actually a lot of flickering between frames and a lot of details are missing. So it does well, but we have so little signal that it's really a waste to treat each frame independently because you have a lot of information across multiple frames. And if you do frame by frame denoising, you're not leveraging that additional information. So we said, all right, well, can we not just do frame by frame denoising, but can we do full video denoising where we process multiple frames at a time so you can leverage information across multiple clips to improve your estimate. But unfortunately, it's really hard to collect a data set like this experimentally because you cannot really collect motion aligned, real noisy and noiseless frames. Because you have to actually like have one camera, you trigger this camera, and between these frames, there's going to be some motion. And so it's very challenging to try to kind of correct for this and realign these clips back to use it for supervised learning. So we said, all right, so none of the off-the-shelf methods work. And whenever we try to train our own denoiser, it doesn't quite work for videos. So can we instead try to train a better noise model so we can have synthetic noisy clips, that we don't have to have any ground truth pairs. We just have our noiseless videos. Then we can simulate very realistic noisy clips from our camera, and then hopefully train this denoiser with synthetic data and see if it'll work on real data from our camera. But the question is, what is the best noise model for this camera at an extremely high gain? And if you take a look at the real noisy images, it looks very different from Gaussian noise, which you see on the right. We have more structured noise. And if we use kind of the best calibrated noise model for low light imaging, it does a little bit better, but still is quite different from the real noisy frames from our camera. Fortunately, what we can do is we can say, okay, I can very easily collect like a large data set of these motionless images where you have these noisy clips and the corresponding noiseless images. But then can we actually use this to learn a noise model where you go from a noiseless clean image to a synthetic noisy image? But this is actually a really hard problem because noise is stochastic. And so if you do this in a standard supervised learning framework, you'll see that, ideally your synthetic noise and your real noise is different every single time. So if you do like a mean squared error loss, which is pixel-wise, you'll get a different number every single time. So instead we proposed not to do this pixel-wise loss, but to actually have a discriminator which would help us kind of learn the distribution of the noise. And so rather than matching the noise on a point-by-point basis, you match the distribution of the synthetic noise to the real noise. So we did this with a GAN, but we wanted to make sure that this would actually work on real data. So we actually constrained the GAN with a few physics-based parameters. So if you take a look at a textbook on kind of the common types of noise you see for a CMOS sensor and low light, there's a few types of noise you'll see. For example, fixed pattern noise. You'll see sometimes this row noise, which is this added offset to every column. And so we're able to kind of parameterize this model. For example, the row noise, we only learn this one parameter, which is a standard deviation of this random offset. And so we have just a few parameters that we learn here, in addition to a CNN, which will help us with anything that we don't actually model. And then we calibrate all these parameters with a GAN, essentially. And hopefully this makes it so it's easy to train and that it'll actually apply to real images. So whenever we did this, here's the image I showed before of kind of the Gaussian noise model versus the best hand-calibrated low light noise model. And then finally, here's ours on the right. And you can see that it much more closely approximates the real noise that we see with our camera. So, okay, now we have a noise model. And then, but really the goal is to also to actually denoise it, right? So we want to then have some sort of denoiser that's trained with the synthetic data and can effectively denoise these video clips. So we kind of just threw all the data we could at this problem. Our camera actually is not just an RGB camera. It's also has an additional IR channel because there's a lot more IR light at night under starlight than there is RGB. But so we actually just took a online data set of RGB videos and we applied our noise model to them in order to generate synthetic clips. And we use that for pre-training. And then we used some real noiseless videos from our camera to augment this and to fine tune, and also some real noisy, noiseless still clips from our camera, just to kind of throw as much data as we could to this problem. And after training, here's some of the results. So here's a raw still clip from the camera. And with kind of the best classic denoiser, it doesn't do so well. You still see a lot of lines. And then with kind of an off-the-shelf pre-trained network, it fails in this case. And then with kind of a single image method is much better. This is actually trained with our own data. But then our method, which leverages multiple clips, multiple frames at a time, does quite a bit better. You see a lot more details in the letters here, and it very closely matches the ground truth. Of course, the real test of this is to say, how well do we do on real noiseless clips where we have no ground truth, where it's extremely dark, so dark that you cannot even see your hand in front of your face? Can we take these, extremely dim videos and see something from them? And so we tried out our denoiser, and if we just kind of contrast stretch our raw clips, you see some motion, but also a lot of noise. With the best classic method, you still see a lot of line artifacts. Single image methods, you see a lot of flickering. Off-the-shelf deep methods, it's just blurred out entirely. And then with ours, we're able to maintain a lot more signal. We see a lot of details here, for example, in the cactus, and we can see the flags waving in the wind. And the thing that I find the most exciting is that actually we're able to capture this fast-moving shooting star and also see these slow-moving satellites going across the night sky. So this gives us a lot of confidence that our denoiser is doing the right thing. We are maintaining a lot of signal, but we're not blurring out the scene. We can still see these, these tiny points moving across the sky, and also these really fast, rare events like this shooting star, which you'll see here. So here's a compilation. Well, here's actually another raw clip and a compilation of some of our denoised results, where you can see this person trying to throw a volleyball, which they cannot even see in front of their face. And here's the Milky Way in the background. And we can see kind of this fast motion. We can see the flags blowing. We can see this umbrella spinning. We can see the people dancing around. And all of this is taken with just a normal CMOS camera, very, very fancy CMOS camera that is, but with no external lights, and in sub-millilux by the light of just the stars. And this kind of goes to show you that, a lot of times off-the-shelf models don't work in real settings. But if you want to really push a camera to its limits, a lot of the kind of linear, well-known models for noise break down. And if you can't easily model it, you can actually try to learn it. And so we showed that you can kind of learn an approximation of the noise model and then use that to synthesize data and really push this camera to its limits. And so I presented this at CVPR actually 2 years ago, and we have all of the data is available online, and there's a project page here. So now I want to actually show you a related but slightly different project where we want to do kind of the same thing. We want to denoise, but for microscopy. And we want to do it in a way that's as robust and as trustworthy as possible. Because for photography, you don't really care if you kind of mess up someone's face or their hand a little bit. But for microscopy, you really cannot hallucinate, because that's going to lead to erroneous discoveries. It's going to be disastrous for medical imaging. And one of the problems here is that, Carl Sagan said that every time a scientific paper presents a bit of data, it's accompanied by an error bar, a quiet but insistent reminder that no knowledge is complete or perfect. And unfortunately, a lot of times, whenever we use deep learning, what we do is we have some sort of imaging system, we have some sort of algorithms, and we get back an image. We do not get back an error bar. And so there's no way to really assess how good this prediction is and how much we should trust it. And this is a big problem because a lot of times deep learning based methods hallucinate because they're designed to. They're designed to kind of give you back these high resolution, high quality images, which means that they're going to give you back these realistic looking artifacts that are not present in the sample. Here's an example here where here's the prediction by the model, and here's the ground truth on the right. And you can see that there's this very convincing looking black line that looks like it could be there, but in the ground truth, it's not really there. And for medical imaging, for scientific imaging, you want to know when this happens. You want to know what you should look out for. You want to be able to trust your prediction. And so in the second part of this talk, I'm going to address these of saying, can we make something that's a little bit more trustworthy? And we're going to really do this by first saying we want to add an error bar to our deep learned reconstructions for denoising. And then we want to see if we can actually use that error bar in a constructive way to drive how we sample and how we take measurements by your imaging system so that you can bring down error and increase your confidence gradually. The application I'm going to focus on here is for scanning microscopy. And basically, the idea here is that you actually scan point by point, because you have usually a high power pulsed laser, and you have a single pixel detector that's very, very sensitive. And so you actually scan point by point across the entire sample to build up 2D and 3D volumes. But with any sort of scanning system like this, you have a trade-off. If you use a really high power laser and you stay at each point for a long time, you'll get great images, but you have a lot of sample damage. And it's very, very slow, so you cannot see dynamic events, and you have a very small field of view. On the other hand, you can stay at each place for a short amount of time, scan really quickly, which allows you to see a larger field of view, allows you to see motion, and to keep scanning over and over again to see dynamic events. But you have worse image quality, which in my opinion is a big advantage, because if you can combat this, if you can denoise this, then you have something that is really compelling because it's so fast and it has a lot less sample damage. This becomes a denoising problem. So essentially, we want to have the same sort of formulation as before. As we have a noisy measurement, or perhaps multiple noisy measurements, and we want to have a denoise prediction. But we also want to somehow quantify how certain we are about each point in this prediction. There's been a bunch of methods that have been proposed to quantify uncertainty in machine learning based denoisers. For example, the most common ones are Bayesian dropout, where you essentially drop a bunch of weights, and you do this n times, and eventually you have some idea of the distribution of the intensity across each point, but this is really slow. And the other method is ensemble techniques, where you train n different networks and each one gives you a slightly different prediction. So you can have some notion of uncertainty from this. But this is really computationally intensive. And it doesn't really give you a guarantee that this uncertainty is a true uncertainty. And so we haven't really seen it widely adopted in the scientific imaging community because it's so slow. You need a lot of GPUs to do this. Recently, there's been another method proposed by Anastasios and Ahmed at UC Berkeley, where they use quantile regression and conformal risk control to predict uncertainty. And this is really, really fast. It's a single forward pass, and it gives you actual rigorous guarantees that the true signal lies within these bounds. So let me tell you how this works. Essentially, in a standard supervised learning framework, you try to train a denoiser to predict your image. And you use a loss, perhaps like mean squared error loss or L1 loss. Now, what we're going to do instead with quantile regression is have your network predict not just the image, but also a lower bound and an upper bound, so that you have this notion of uncertainty from this. And the way we do this is for mean squared error, this is a symmetric loss. It doesn't matter if your prediction is too big or too small, you have the same loss value. But for quantile regression, you have this asymmetric loss. So you can skew the value. So if it's smaller than 0.5, it's 0.1, for example. If your predicted image is bigger than the true image, you'll have a much larger loss value. So this is going to encourage your estimate to be smaller than the mean. On the flip side, if your alpha is larger, it's going to heavily penalize underestimates and get the network to predict something that's bigger than the mean. So this essentially will give you your lower bound and your upper bound. So you have a modified loss for your network, and then you'll get back your image prediction, a lower bound, and an upper bound. But can we trust these bounds? And so you have to have a second step. After training, you have a second calibration step where you say, I'm going to have a held out calibration data set, and then I'm going to use this to scale the bounds to make it a little bit bigger or a little bit smaller until, say, 90% of the true signal lies within those bounds. And after you do this, you have this pre-trained network that will predict a lower and upper bound. You'll calibrate those bounds for a new data set of your choosing, and then you can have something that is really fast and gives you guarantees. Okay, so we tried this with multi-image denoising, and you can see here's the predicted image and here's the uncertainty. And if we use more than one image for denoising, you can see that the uncertainty goes down and the denoise prediction becomes more clear. What's more exciting here is actually, if you zoom in on this one region of the image, you can see that here's the measurement and here's the denoised image. The denoiser produced this sort of ring, this ring feature here, which isn't present in the ground truth. And our uncertainty map shows that this region is red, which means it has high uncertainty. And if we use more than one image for denoising, this ring artifact goes away and we converge to the ground truth image, which I think is really compelling. It shows us that uncertainty actually catches a hallucination. And by using more signal, we're able to remove this hallucination and do a whole bunch better. You don't have to train and calibrate with the same data set. So here we actually tried this out on a home-built multi-photon microscope, and we just had only like a 20-image calibration data set to calibrate these bounds, and we showed that this actually still works, and we're able to actually pinpoint hallucination here, and after multi-image denoising, that hallucination goes away. Now, the thing that's really exciting is once you have these error bars, you can use them in the loop to do something really exciting, which is adaptive acquisition. So the way this works is you say, okay, we're going to scan this entire region, denoise the image, get back this uncertainty map, and then you can go back, you can kind of threshold it by the uncertainty and only rescan the most uncertain regions of your sample, which means you actually use a lot less light and you can scan much, much faster than before. Of course, this is kind of sample dependent, where if your sample is more dense, you probably have to rescan a whole bunch of it. But if it's really sparse, you can save a lot of light and only rescan a few of the pixels. Okay, I think I'm running out of time, so I just want to summarize that in the uncertainty-driven adaptive acquisition, what we showed is that you can add an error bar, and then you can actually kind of rescan and resample your measurement in a way that's both algorithm and sample informed. And this has the potential of allowing you to scan much faster, and you can have a lot less light dose to your sample. We are showing this all in software. We're in the process of collaborating with some neuroscientists to try to actually show this in the loop with some real hardware and hopefully extend this to 3D and dynamic samples. Okay, so with that, I'd like to conclude. I showed these two different projects of learning noise models and also trying to learn error bars for denoising. I would like to acknowledge the Waller Lab at UC Berkeley for the first project, along with Vladimir Colton, who I did an internship with at Intel Labs, and then the Yo Lab at MIT with Cassandra Yi, who did all the uncertainty work. A quick pitch, I'm starting a new lab at Cornell, and I'm looking for collaborators, postdocs, PhD students. And with that, I'm happy to take any questions.
Okay, all right, thank you. Let's thank our speaker. All right. Yeah, really, thank you for the great talk. Are there any questions for Christina? Oh, we have one. I'll tell you what, you want to just come up here and say it? Just so then you can just really say it the way you want, you know? Yeah. All right. All right, all you?
Hi, Christina. Thanks for the great talk. Just want to ask a question regarding the camera that you used in the first project. Was that like it was a regular CMOS, but was that a converted monochrome, or was that with the bare array on it?
Yeah, great question. Let's see if I have this. Okay, so yeah. So basically this was a Canon CMOS camera that had this modified RGB NIR Bayer pattern. So it had, RGB and then IR, but actually every channel had IR. And so if you want to get back the RGB image, you actually just subtract out the IR channel. So it's basically a modified Bayer filter that also has IR.
Right. Thank you.
Mm-hmm.
Any other questions? Oh, you do? Okay, yeah, come on. There we go. One more. All right.
Thank you. Very interesting talk. This is Ali from Purdue. In this project, you're shooting a lot of the scenes are towards the sky and the stars. So even the objects, the humans are they have a background, a star night background. Do you have, or did you experiment with scenes where maybe you face the other way, where you did not have the star background, basically?
I think the majority of the scenes we have the stars in the background, and that's because that was kind of one of the most interesting features that we could see is we wanted to show the Milky Way in the background. We
Okay.
wanted to show some shooting stars. Actually, during training, we don't use so many images with stars. We actually train mostly on daylight scenes. So I think that this should work on more natural scenes. And some of our still objects were, very, very different from this. If I go back to our still objects, so sorry, let me go back. Yeah, so here, for example, this has no stars. And so, the algorithm should be, it should work on that, but our data set mostly has images with a star background.
I see. Thank you.
All right. Are there any more questions? Otherwise, I think we'll probably just thank the speaker one more time and then move to the next one. So, all right, let's thank the speaker.
Thanks.
Okay, yeah, thank you, Christina. All right, cool. Okay, so. Yep, so we have one more speaker. Let me download the slides while I'm talking here. But so our next speaker is Minchul Kim from MSU. So let me download his slides. I'm not sharing it. Okay, cool. All right. And then I'll say a little bit about Minchul. Hang on, I have to move. All right, there we go. I have all the Zoom stuff in front of me. I couldn't find it. Okay, we're good now, though. All right. Oh, you know what it is? It's my laptop wasn't refreshing the emails. That's what was happening earlier. I don't know why not. Hang on, I might have to manually refresh it. Could be that too. Yeah. Yeah, that's not, huh, that's so strange. Let me send it to myself on a different website, a different way. Okay, so but while I'm sending this to myself and handling all this, let me introduce Mitchell. So the previous, let me make sure I'm not, yeah, okay. So I actually know Mitchell to some degree fairly well. Okay, so I guess I have a comment about him. So when I first like ever met Mitchell was over Zoom, and I thought to myself, like, wow, this guy, he's really a great speaker. And I just assumed the way that he was speaking, he was reading off of like a script like the whole time. It was just so coherent. And well, now I've seen Minchell give a number of talks, okay, and it has nothing to do with that. He's just a wonderful speaker, okay. So that's the first thing I wanted to say. He really is just a great speaker. And then the second thing I'd like to say is that he's working with, as I said, Anil Jain and Xiaoming Liu from MSU. He's doing facial recognition and also generation as well more recently. So as I'm pulling it up here, I'll just end with saying that really looking forward to this last talk, and then we will go on a break and then come back at 11. There we go. And then we will just conclude with the final remarks as far as who won the challenges and all of that good stuff. So hope to see you after this last talk. So this should be coming to me any moment. I just sent it to myself. Let's see. Yeah, I don't know what's happening with my emails. I'm afraid to click any buttons. I'll tell you what, Mitchell, is it okay if you just do it on your own laptop? Is that okay? Maybe, this happened earlier. I thought it was like, oh, it's just the speed of email, but it's the speed of my own computer. I don't know what it is. So, okay, yeah, I'll just ask you to present that. I'm sorry about that. Yeah. That's okay. I'll set this up so you don't have to worry about that. Yeah, yeah, cool. I'm sorry about that.
No.
Do you need this adapter?
Yeah,
Yeah,
for sure.
okay, I'll leave it to that. Yeah. All right, yeah. So let's welcome our speaker, Minchul Kim from MSU.
Hello guys, thank you for the introduction. I was going to read off of a script. Somehow I'm a little bit more pressure to be engaging. Thank you for the introduction. I'm excited to speak here at the 7th UG Challenge. The title of the talk is Face Recognition with Low Quality Imagery. This is a project that I've been doing with Michigan State University and IARPA, with a project that is involved in biometrics for the low quality actor. So to give a brief overview, face recognition is a multi-step pipeline where it starts by detecting a face and it aligns it to a canonical position like that. And the model extracts a feature vector from the aligned image where during training it is sort of supervised most of the time with a labeled data set and it's posed as a classification. So it is to a lot of people, it is a very simple pipeline, alignment and then classification. But for face recognition with low quality imagery, then it becomes a little bit more challenging because of the information content is missing. So we, in this talk, try to answer this question: how do we better conduct face recognition under low quality imagery? And we'll start off with this paper, AdaFace, which tackles how do we design a loss function to better train a model that's suited for low quality imagery. And then we'll move on to work in feature fusion, where you're moving on from an image paradigm to a video paradigm. And then we'll end with recent work, which uses facial key points to do better face recognition with those image. Firstly, we'll talk about this paper AFace, the loss function for face recognition. The problem definition involves noticing that some images are more identifiable than others. Here are some degrees, varying degrees in identifiability of some contributing factors. And some training data that are shown here, arranged from top to bottom according to the identifiability. Notice that at the bottom we have some hard to recognize images. And this is generally unidentifiable images, and this poses some problem for model-driven training, because these it is impossible to extract any good information from these kind of images. And we propose a new loss function to handle these images. To tackle this question, we consider the sample importance during training. Conventionally, training samples are treated equally: easy samples, difficult samples, or hard samples, without deliberate change in their weights. Some works, since the birth of deep learning, have acknowledged that hard sample mining or curriculum is important, and therefore some works do try to overweight the hard samples. However, hard sample mining puts a strong emphasis on unidentifiable samples. It's because unidentifiable samples are naturally also very hard samples. So we aim to put an unequal emphasis on samples of different difficulty by emphasizing hard samples while avoiding unidentifiable samples. And how do we do this? When looking at the samples, we introduce one more dimension to the table, and we hypothesize that the distribution of sample is different based on the image quality. Namely, the low quality samples will contain more number of unrecognized images. It's a pretty weak assumption. And what do we do with this? To put it another way, we want a loss function that puts large weight on hard samples for high quality images and smaller weight on hard samples for low quality images. And to achieve this, here's an overview of the proposed loss function. We modify the cross entropy loss by adding adaptive margin function based on the image property. There are two parts to this. We first show how margin functions modulate the emphasis of training samples, and we will also show how we approximate the image quality with feature. So here is a depiction of the normalized softmax loss often used in face recognition. It's a variant of softmax loss often used in classification, but each arrow is a sample's embedding vector Z, and the red line is a decision boundary that's created during training. And the angular distance to the class center is the difficulty of a particular sample with respect to the model being trained. So the farther away from the class center, then during the training to the model, it is a hard to fit image. And there are two types of margin functions: additive margins and angular margins. Both shifts the decision boundary closer to the center. The question we ask is, how do they differ in their gradients or their gradients magnitude? And we try to analyze that. And we find that they have some contrasting behaviors between the angular and the additive margins we have. So by taking the partial derivative with respect to the loss, we find that the margin function f affects the first two constant terms, which we name gradient scaling term G. And we plot G on the feature space with color here. And we show a scenario here. There is no margin of 5 here yet. This is for I'm trying to illustrate the plot. Samples near the class center gets no learning signal, which is blue. And the samples past the decision boundary has large G, which is red. With the additive margin, now the decision boundary is shifted. More samples receive learning signals, but their gradient scaling term here is similar to one another. So it's flat regions. So the flat red region signals that
regardless of where you are past the gradient, past the decision boundary, you get the same magnitude of the loss. However, with the angular margin, we see a different behavior. When M is bigger, the margin is bigger, the samples near the decision boundary gets larger gradient term than the samples far away from the decision boundary. So it shows that the angular margin modulates the emphasis on samples based on their difficulty. So we can use this property. And if M is smaller than 0, then we can achieve a reverse effect as well. So we try to use this property to design a new loss function that we can modify the emphasis of samples as well. So combining it all, we adaptively vary margin functions based on the feature norm. G angle and G add are margins that change with the feature norm. We combine them in such a way that hard samples are emphasized when the feature norm is high, as indicated by the black triangle there, the small triangle. And we de-emphasize hard samples when the feature norm is low, as indicated by the white triangle. So conceptually, thinking of eta phase is as differentiating margin function based on the feature norm as shown. And we try to show that its efficacy in various data sets. First, we take some high quality image data sets, and we try to compare this with previous face recognition loss functions, such as cosine phase, arc phase, particular phase, so on and so forth. And for the metric, we use one-to-one verification. So in the high quality images, as you can see, it's sometimes win, sometimes lost. And on average, it's a very close call, so there isn't much improvement in high quality data. And we move on to the mixed quality data set, which is shown over here. Some images have low quality imagery, and some images have high quality. For metrics, we also use a TAR and FAR for 0.01%. And for the beginning with mixed quality images, we begin to see some noticeable improvements in these performances. And then we lastly move on to the low quality data sets where we observe the biggest improvement. Yes, and we believe that it is because the model is trained to handle the low quality images better by filtering out the images that are impossible to learn, but while trying to focus on the hard samples that from the low quality images. So that's the end of the first work, and we'll move on to the feature fusion paradigm. So moving from image to the video face recognition. And this is a work from a work called clustering. First, I would like to contrast the difference between face recognition with image and videos. Here we show some common scenarios with images, where you have a probe image and some gallery database. And the feature-based face recognition uses a pre-trained face recognition model to create a high-dimensional feature vector for each image, whose similarity measure could be used to identify the most similar person in the gallery. So it's a cosine similarity that's used. But for the videos, it becomes a little bit more complicated. Here we show a probe video from our own data set with a 30 FPS. A relatively short video of 90 seconds generates about 2,700 frames. And on the bottom, we show some keyframes, and the face is extracted from each frame. And as the example shows, there are only a few good images that combine meaningful identity information. And furthermore, the length of the video could also vary. So video-based face recognition contains few traits that make it more challenging. Number one is each individual frame has varied identifiability. And secondly, the number of frames can vary and be very large in number. Some videos can be maybe 5 to 10 minutes, 30 minutes, and the number of images there can go up above 3 again. And we also want this model to be deployed in the live setting where the frames can also come in sequentially. This raises an important question of how do we utilize past frames when one more frame is added? Do we run a bank of top K most influential images, or do we store everything maybe million feature vectors, and we use all the frames every time there is a new frame. So to do this well, practical face recognition model will check off these points. It is a it is able to model the intra-set relationship, and it can handle large probes, and it is efficient in sequential inference. For introducing our work, we first recap what usually feature fusion model does. It is a mapping from an arbitrary number of inputs to a single representation. And naively, when we do this, we simply have a network that tries to average this together. And in the scope of our research, we let the feature extractor be fixed. So there is no training for the feature extractor, but we're looking to learn the fusion factor. The most intuitive way to perform feature fusion is to do averaging the features, or weighted averaging the features. But since some features are better than the others, some works perform quality estimations. This leads to weighted averaging scheme. But the problem with this approach is that there is no intra-set relationship. So each image does not know the quality of other samples. Second one could consider a model that takes all the inputs concurrently, like a transformer does, or the attention mechanism. This design can model intra-set relationship. But the problem with this approach is that if n becomes too large, the computation becomes infeasible, making the model unsuitable in most videos. So our proposed approach is a paradigm that could be explained in this diagram. First, the inputs from 1 to n are arbitrary number of inputs. And secondly, we cluster them to a fixed number of features, f1 prime to fm. The number of intermediate representation is a fixed quantity. And then the subsequent aggregation network takes the intermediate features to produce a single fused output. So let me give you an illustration. So we divide the fuse into smaller batches. The first 4 samples are clustered into 3 intermediates. And then the next 4, after discarding the first 4, could be fed in and update the intermediate. And then we can repeat this until we run out of the samples to process. So this is an overview of the whole pipeline. It comprises of 3 components: style input maker, cluster network, and aggregation network. And let's talk about each component one by one. First, we use the fixed pre-trained feature extractor to extract features, and we feed the input image of arbitrary into to get the feature F. And then secondly, we extract the style of an image, which will be useful for determining the quality of each prediction. So the style is defined by the mean and variance of the intermediate features. And then the style features and the features are clustered using cluster network. The purpose of the cluster network is to self-assign the styles and the identity vectors of length n, so fixed length of n. And we learn a global shared cluster center whose similarity with style governs the assignment of features to each cluster. And then the last part is the m intermediate features are given to the aggregation network to produce a single fused output M. The aggregation network maps a fixed shape feature into a single vector, so we can use MLPs. And when the input is sequential, we divide the input queues into multiple batches, and we infer them sequentially. In that case, we store the previous intermediate outputs. We update them with a goal that is invariant to the order of batches. The update goal is used to is an incremental averaging, and which is invariant to batches. So every time the new batch comes in, we update the intermediate, and then use the aggregation network to update the final. So for training, we use 2 kinds of losses to train the whole thing end to end. First, we use a simple cosine similarity between fused feature and the class center. And then the second loss is we further add a permutation invariance loss, which reduces the distance between the fused feature and the permuted fused feature. And the performance using CA-based compared to the previous methods is shown in this diagram where we try to highlight that it is a lot more beneficial to use some sort of a in context aware feature fusion model. But if we don't use the two-stage paradigm, then it is impossible to handle large number of probes. So for instance, we show 4 different data sets of different probe sizes. IJBC has on average 23 images per probe, but IJBS has about on average 7,000 images. And some of the promising methods such as RSA, which is using transformers to do feature fusion, cannot handle it, therefore the performance. And we try to analyze what happens with the assignment network. This is a visualization of the learned assignment weight. And each image is assigned to one of the intermediate clusters. So each column sums up to 1. And you can see that the first image is assigned to cluster 1, softly assigned to cluster 1, more so than the other clusters. And each cluster is formed by weighted averaging the row. So as you can see, the cluster 1, which is the first row, has many of the high quality images, whereas the cluster 4 on the bottom is filled with a lot of the low quality images. So cluster 4 we see is sort of acting as a garbage collector. And here is a depiction. We want to show a comparison of CA phase and the simple averaging. On the bottom, we have a simple averaging where the colors indicate the feature norm. So when you're averaging features, the norm of the feature governs the contribution of those features. So we're plotting the feature norm. And as you can see, the higher norm features are closer to the right, which is indicating that these images are closer to the gathering. And on the top, we have CA-based features where it is contrastingly different by selecting only few ones by the red colors. And the star indicates the fused feature. And we see that the fused feature is actually outperforming any of the individual features. So this is a illustration of what happens in practice. As video rolls in, the detected faces get to be fed to the face recognition model. The individual dots represent the individual feature vectors, cosine similarity to the actual ground truth gallery indicated on the bottom right. Note that many bad quality images become registered, and they push the averaging scheme, which is the yellow dot, to be on the left side. And then if you try to select most influential frames by CA phase, then that produces a fused feature that is to the far right. So that's illustrating the benefit of using CA phase. And now we move on to the last part of our work, the recent work KPRP, and it is titled Key Point Relative Position Encoding for Face Recognition. So what we start off by asking, what is a vision transformer and how do we use key points in improving the feature extractor? Vision transformer is a stack of transformer that takes the patch of images as token. We want to highlight that there is a multi-attention module, which is a UK transpose. And previous works have shown that adding a relative position encoding here it helps a model by learning, injecting a prior information, such as nearby pixels are more important than the far-more pixels, like CNN. So in equation, without RP, it's something like that in the attention score. But with RP, then you're learning an offset value Bij that is being injected. Bij is a learned value for unique Curry and key location pairs. For example, B12 is a function of location query 1 and key 2, and B34 is a function of location query 3 and 4. Note that the function takes in the location, not the feature itself. So therefore, a suitable function could be a distance between query and key. And once the value for all the query and keys are computed, then we can create a B matrix, as shown over there, and add it to the attention score. The phenomenon we're trying to address here is the issue. What happens when query and key relationship is the same for all images of different semantic meaning? So for example, for these 3 different images, as we are computing the relative position encoding, the actual meaning of individual offsets actually differ because the content of the image is different. But so RP is good enough to inject prior information such as nearby pixels are important, but it's not good enough to control the importance based on the semantic context. So we try to make it more dynamic by adding in the context to the RP. And the way we do this is by making the RP as a function of not just query and key locations, but the key point locations. And the way we do this is specifically for a given query, we compute a distance to all keys. And this is equivalent to a normal RP. We take the distance function IRP and apply the quantized distance. So the individual colors imply same distance. And the direction also matters. And then we optimize what actual value to each color or distance should represent. So for instance, the purple could be 0.5 and blue could be 0.2. We formulate this as a linear function of the distance between the key points in the curve. In other words, the static value dictionary of RP becomes a function of key points. And then for each query and key pair, the actual value depends on both the distance between query and key and the location of key points. So what are the key points? The key points are shown here. It could be facial landmarks or body skeletons, or even for simple images with black and white, it could be a proper impossible. And we try to show that by adding in this key point element to the relative position encoding, it brings affine transformation robustness to the model. So training data set is MNIST, and test data set is an affine transformed version of the MNIST. And then we compare different versions of the RP. And by using the key points in the way in which KPRP uses, the model is actually performing the best, indicating that the model is more robust to the affine transformation when we use key points. And we try to show that benefit carries over to face recognition in low quality imagery by evaluating in low quality imagery data sets, and the performance gain is shown here. So yes, so this is a recap of the talk. We explored how to adjust the loss function during training to better handle the low quality images. We also talked about how to do feature fusion with 2-stage assignment mechanism. And lastly, we talked about how to use the key points to make the model more robust to low quality images. And that's the end of my talk.
All right, so just as always, are there any questions from any of the, yeah, sure, go for it.
And the relative position embedding that you've added, is it not eliminating the alignment step that you need to do on the first step?
Oh,
Or you can use it instead of alignment, or you need to align and to do that?
I see. So that's a good question. So when we have a detected face, the first step for most of the face recognition models is to align it in the canonical position. The backbone with the KPRP is also taking in inputs that are aligned, because the model has seen that image more often. But it is the point of the paper is even if you add in images that are misaligned, so some misalignment could happen during this alignment stage. Even if that happens, it is still robust to that misalignment. But that's the takeaway message. But the performance we're measuring is with the aligned. We try to align it as much as possible.
Any other questions? I have a question also, which is, okay, so I'm not very, I'm sure it's no surprise to you, okay, but I'm not very well versed in terms of facial recognition. So my question to you is like, when I've heard you talk about like the loss function design of Ada face, to me that sounds like the right thing to do. You know what I mean? And so my question to you is, do you see that there is some case that Ada face, because it tends to work for clean data essentially just as well as like a standard metric. do you see that there's something that Adaface is severely lacking on? Or do you feel like that it's near sort of the, let's say, optimal loss function design?
I see. That's a very great question. The strong assumption that Adaface is making is that the the feature norm correlates with the quality of the prediction. That usually happens with the softmax loss because the maximum softmax operation allows the feature norm to grow if you have confident prediction. But it's not always the case, and I have observed that with many of the recent VIT models. So the higher the feature norm doesn't correlate with the confidence of the feature. So you can get a lot of the bad predictions cluster in the high norm features. And in that case, the assignment of different margins based on the feature norm is really disastrous. So the better quality estimation or maybe analysis on why such things happen in the architecture could also be important.
Okay. Yeah, that makes sense. That makes sense. All right, excellent. Any other questions?
I was gonna ask about the same thing as regarding basically this adaptive weighting scheme that you have. So there's a number of existing works such as, let's say, focal loss being one of the more popular. And focal loss operates in the alpha space as we measure and the difficulty literally of the sample stuff. How about, repurposing what you've done in the case of checking these feature norms instead, but putting for something like focal loss where you focus more on how well you do instead? Because that is where the supervision signal is coming.
I see. That is actually a good point. So the loss itself is an indication of how well the training is doing for that particular sample. So I think we could go with the loss or the value of the loss as an indication of whether it is a high quality or the low quality, but it is one way or the other, the feature norm or the loss, it is still a correlation to the quality of the image. So we actually, so the loss function is to me more like whether the model has actually fitted that image, particularly at that point in the checkpoint. Whereas feature norm, I was hoping it was working as actual proxy for the quality of the image. So that's why I use the feature norm. But I think now that the other architectures have shown that the feature norm actually doesn't sometimes correlate with the prediction quality of the image, then I think that assumption could be faulty. And using the loss function, loss value as a proxy could be a way to do it.
Thank you.
All right. Well, let's thank the speaker one more time for a great talk. And then, so we're going to take a break. We'll come back at 11, where we'll just discuss the results of the challenge. So, all right. Thank you, everybody. All right. Great job. Let me pause the recording here. Recording in progress. Okay. So I'm just going to, let me see. Sing-Wong, would you want to do the results or do you want me to do it? I already have it. Huh?
I've been.
Cool, yeah. I mean, I was like, yeah, I'll cool. All right. I know I'm just throwing you on the spot. Sorry, but I was just figuring out to ask. Okay. By the way, since this is, I think it's recording, for the record, I should say, if anyone has had, this goes to the people in the challenge, if anyone has had a positive experience in the course of, I don't know, engaging with this challenge, okay? That probably has nothing to do with me. It probably has everything to do with all of the other professors and students, okay? And then I'll make one final comment, which is, if you've had a negative experience, that probably had to do with me, okay? So then that's my whole opening spiel about the challenge, okay? So it really comes down to these other teams really did 99.9% of the work, okay? So I absolutely have to acknowledge that. And that should be on the recording, okay? So it's official then. All right, so let's go. So that's the schedule. Just remind you of the challenge tracks very briefly. We have a challenge track in imaging through turbulence and downstream computer vision tasks. semantic segmentation, and also UAV tracking and pose estimation. So just to highlight the results for track, there's actually two subtracks for imaging through turbulence, which I kind of briefly described earlier. For doing image restoration and then downstream text recognition. The top three performers this year are Team DPT, Thankful, and NJust KMG. You can find full details of this on our Coda, there's a Coda Lab page. One thing I wanted to highlight is that their performance is insanely close, okay? And if you compare that to last year's results, there was more of a distribution and they were also lower. I'll comment as to why I think, for one, the top three has improved so much, and two, the results are so close. I'll do that in just a moment. The next track is track 1.2, coded restoration through atmospheric turbulence. Again, nearly a three-way tie. And when I saw this, I thought, okay, then I think there really is something going on here. Not fishy, okay, but just something going on. What is it? I think I have an answer, maybe as to part of it, why it is. So the goal here is to reconstruct some sort of essentially QR code, and then compute some sort of error metric based on Hamming distance. So the top three performance, DPT, I think, won both. So DPT, IPIU GXJ is second, and then Obsidian is third here. Again, close performance last year. Close performance, but they've all improved, okay, from last year to this year. So my overall impression is that what's the biggest change as far as the challenge is concerned? In fact, much of the data is the same. Some of the testing is different. So what's the big change, okay? So last year we gave people the turbulence simulator version 2, okay? This one, Singwang, that's probably like 2020, right? Version 2, 2020-ish, yeah. And some validation data to just like test their stuff out. So, but this year, what we did was we still gave them the turbulence simulator, but we said, hey, maybe you don't want to mess with all that. We'll just give you 200 gigabytes of training data. And this is from either version 5 or version 6, I couldn't remember. But so this is extremely recent. This is 2020, late 2023-ish, probably, right? That's probably sounds about right. I think so, yeah. I sort of get all the versions. They blend together at this point, you know what I mean? Huh? Yeah. But so, and then also we have, Singwang has two open source methods, one which is turbulence mitigation transformer, and then the other one is Datum, which he'll give a poster presentation at CVPR this year on. So Datum is the one that if you saw me do that back and forth with the image quality improving, that was the Datum one. So I think this has had a big, if I had to boil it down to one thing, if I had to make a guess as to why the improvement has gone in the way that it does, it comes down to this, which I think matches our experience in our projects, which is more data, better data tends to give better results. Especially good synthetic data, okay? So, all right, that is my comments about the turbulence challenge, and then I'll give it to, I think, Howard for the, okay, yeah. Let's do this again. Give me just 1 second. I don't know, it's being, every time I do that, I'm not like okay, so I have to admit, okay, I'm not like a real Mac user, I'm like a fake, all right? I just got this like 2 years ago, and I use it very rarely. So I'm like a fake Mac user. Okay, so I don't really know all the tricks. All right, sorry. I just know how to quit. That's like the main thing that I know how to do. Okay, I know quit and I know go back and forth between screens. That's like all I know. So okay, all right.
That's basically all I know too. So, all right, cool. Yeah, so brief, like some statistics about the challenge. So what we provided them was a training set of 148,000 paired, degraded, and clean images for training. And for the dry run, kind of the validation, we had 26,000 paired, degraded, and clean images. And then for the final testing set, we gave them 6,000 degraded images. Here's some examples from the final testing set you see here on the right side. Yeah, and a couple notes. I think for the number of submissions that we gave, I think that was the number of like final teams that submitted. Yeah, so just as a final note, I think we had around 740 like submissions, like those 12 people submitted that number of times. So yeah, cool. So I'll read out the team names for the people who won. So team number 1 is team Jiangnan. So each of our submissions have like a paper that details their methods, their like data augmentations that they use, data sets that they use, and like things like that. So I'll also read out the paper name so everyone can check out the paper if they want more information on the method. So Team Jungnan wrote enhanced semantic segmentation pipeline for weatherproof dataset challenge. And they got an MIOU of 0.47. And just like the other challenge, actually, the top 3 places are all very close in their MIOU. So yeah, congratulations to all of them. Rank 2 is Team New Boy. And their paper was technical report for CVPR 2024, weatherproof dataset challenge, semantic segmentation on paired real data. And team number 3 was ZZYYXXZNB. And their paper was solution for CVPR 2024 UG2 plus challenge track on all weather semantic segmentation. So congratulations to the top 3. And thank you for all the participants as well. Cool. So just a couple notes as well on like the trends that we're starting to see with a lot of these challenge track submissions. So in terms of architectures, we see like basically every single person who submitted used some sort of foundation model, what I would describe as foundation models. See models with like hundreds of millions or billions of parameters trained on hundreds of millions of images. These ones it really tells me that these sort of like priors that they learn on like hundreds of millions of images are really something that you need to take advantage of when you do some downstream tasks like semantic segmentation. So when we try to fix our models for degraded weather, what we want to do is try to manipulate and modify these architectures to make them work better for degraded weather conditions and degradations in general, and not just try to like replace the model entirely. So also we saw some interesting methods such as using video deweathering. So low rank tensor recovery is a method that some people used to get pseudo ground truth kind of to aid in the deweathering. Data augmentations, besides just the classic, like flips and rotations, some people use super resolution, so another form of image restoration to help. Synthetic weather effects like rain, fog, or snow, kind of feeding into the idea that the more data that you have, the more it helps with these sort of challenges. Language guidance was a big one. So we actually wrote a paper on using clip language priors to help with semantic segmentation in degraded weather conditions. And this is something that some of our challengers picked up on, and they used these clip language priors as well. And they actually improved it by using not just weather language like rain or fog or snow or haze or something like that. They also used semantic categories, blended these clip context vectors, and they also saw some improvements in that aspect as well. So language priors is another thing that we can kind of take advantage of to help with these challenges. So yeah, congrats to all the winners.
Thank you, Howard. And then so the last team is the 2 teams from Singapore. So unfortunately, they were not able to get to CVPR this year. So I'm just going to very briefly detail their results of the challenge, that is. So let's go here, whatever. All right. So again, just to remind, there you go, everybody. So the goal of this challenge was basically given a crazy amount of multimodal data. Okay, so again, just to go over it, because I think they've done a great job of collecting real data. They have millimeter wave radar, audio array, stereo vision, peripheral 3D LiDAR, and conic 3D LiDAR, as well as this Leica thing that might be, does anyone know, is that LiDAR? I actually don't know what that is, to tell you the truth. And then maybe 2 fisheye lenses, maybe that's one of them. The goal of this is to do a couple things. One is to track the UAV, another is to estimate the pose, and then the final is potentially to recover which UAV drone it was. So they actually have a few different UAV drones, they have different flying patterns and so on. And the goal is to sort of use all of this crazy amount of data and correctly classify the things that I mentioned. Okay, so that's the goal of this challenge. So I'll just briefly go over here. They actually had quite, I think, a decent distribution of scores compared to, I guess, the 2 other challenge tracks. But okay, so the number 1 participant is SDUCZS. and they had an extremely low, at least relative to other people, MSE loss. And their UAV classification accuracy was extremely high compared to other people. And then second in place was Galfin Lab and SYSULT or TT, I actually can't tell. And then Castris and NTU ICG were then the runners up. So yeah, unfortunately, I wish they could be here. That I'm sure they would be happy to give more details. But you can find a ton of details on their website and on their Coda. They don't have Coda Lab; they do Coda. It's like Coda Link or something like that. But they have a ton of details on which you can find through the website on their challenge. So, and I would encourage you to check their data out because I know they really took a lot of time to collect it, and hopefully they do more stuff with this multimodality data set acquisition. So, okay, that will be I guess the end of the workshop. So thank you everybody for your attendance and paying attention and all of that. And hope you enjoy Seattle and the rest of the CPR. So yeah, thank you.